Hey everybody, welcome to this video, and this is a video about motion with constant acceleration where I'm going to introduce you to the kinematic equations. Now, these are one-dimensional kinematic equations talking about going in one direction. This is constant acceleration, which means you are constantly changing speeds. That's all acceleration is. You're either going faster or you're slowing down. It's constantly changing speeds. And for those equations, for those problems, we'll use these three equations right here. And you'll know when the time's right to use each one because of what's listed in the word problem. You'll narrow it down to what you need to solve for. Okay, if we look at this first practice problem, it says a ball is thrown straight upward with an initial velocity of positive 8.2 meters per second. If the acceleration of the ball is negative 9.18 meters per second squared, what is its velocity after half a second? Now, if you notice, there's positives and negatives in this problem. We like to view the upward direction in physics as positive and the downward direction in negative. So if you're throwing the ball up, that's why it has an initial velocity of plus 8.2 seconds, 8.2 meters per second rather, and gravity is pulling on the ball in the downward direction, which is where the negative 9.81 meters per second squared comes from. So in order to solve for a problem like this, you have to pull out your variables. What do I know, and what is it giving me, and what am I trying to solve for? So for this first one, it gives us an initial velocity of plus 8.2 meters per second. So I'm going to write that down on my sheet over here, and we'll click over in just a second. Okay, and then I'll look up again and see that it also gives us acceleration for this problem. It gives us an acceleration of negative 9.81 meters per second squared. So I will write that variable down. And I'll also write down the variable for time, 0.50 seconds. So that's time. And it's asking me what is its velocity after that. So I'm looking for final velocity. So let's look back at the kinematic equations. It's asking me to solve for final velocity, and it's giving me the initial velocity, the acceleration, and the time. Well, if you look at these, let's look at these second two first. There's a distance. There's a distance. Well, it didn't mention anything about distance in this problem, so those two are out, these are in. So we're going with these. So it gave us initial velocity, acceleration, and time, and we are solving for final velocity. So let's flip over and look at our sheet. And I've already written down our variables that it gave us. And final velocity is what we're solving for. So we don't know that yet. And here's the equation that we will use to solve it. The final velocity is equal to velocity initial plus acceleration times time. So now it's just a matter of plugging these in and solving for this problem. So velocity equals the initial velocity, which was 8.2 meters per second, and if it's a plus, I don't need to write the positive sign. I just need to make sure I write it if it's negative. So 8.2 meters per second is how hard we threw the ball in the upward direction, plus the acceleration, which is negative 9.81 meters per second squared, times time, which was 0.50 seconds. Okay, now it's just a matter of solving because I have the variable I want to solve for already isolated by itself on this side of the equation, so now I'll just go ahead and solve over here. So let's do that. We have 8.2 plus negative 9.81, times 0.5. And that equals 3.295, which we could just say 3.3. So our final velocity after half a second is equal to 3.3 meters per second. And just so you know that we used the units, that we had the units correct, that they came out meters per second, because here you have meters per second, but here you have meters per second squared, and then you have seconds. you can't add units that aren't alike. But here's where they become alike, because we have seconds here and we're multiplying. This is on top. These seconds are on the bottom, and it's seconds squared, so that one of those will cancel out, so it'll just leave that in meters per second. So meters per second plus meters per second will equal meters per second. So that will be your final answer for number 1. After half a second, if you throw the ball in the upward direction at 8.2 meters per second velocity in the upward direction, with gravity pulling on it at 9.81 meters per second squared in the downward direction, after half a second the ball will slow down to 3.3 meters per second in the positive or upward direction. Okay, our next problem, number 2, a boat moves slowly inside a marina with a constant speed of 1.50 meters per second. As soon as it leaves the marina, it throttles up and accelerates at 2.40 meters per second squared. A, how fast is the boat moving after 5 seconds? And B, how far does it travel in this time? And this time referring to the 5 seconds. So it's got a two-part problem. Let's look at what it gives us. It gives us the initial velocity, because it says a boat moves slowly inside the marina at a constant speed of 1.50 meters per second. That's initially how fast it's moving. 1.50 meters per second is initial velocity. Then, as soon as it leaves the marina, it throttles up and accelerates. That tells you, it gives us acceleration, 2.40 meters per second squared. And it gives us the time after 5 seconds. So we have initial velocity, acceleration, and time. And then it's asking for how fast the boat is moving after the 5 seconds. So it's asking for the final velocity. It's after. So once again, we're going to use the same exact equation we did before, because distance is not involved in this problem. So these two are distance. This one does not involve distance. So that's what we're going to go with. We're going to solve for final velocity. It gives us the velocity initial, acceleration, and time. So if we go over to a sheet already, I have it written down. And here's our initial, acceleration, time, and we're solving for final. We'll use this exact equation. I'll go ahead and plug those numbers in. Velocity initial is 1.50 meters per second, and we're going to add that to the acceleration times the time, 2.40 meters per second squared, and time is 5 seconds. So once again, just like the last problem, as we do our math, seconds on top will cancel out with one of the seconds on the bottom, so we'll be in meters per second, meters per second. So let's get all this together and we'll find out what our final velocity is. And we got 1.50 plus, and we have 2.4 times 5. Oops. I am fumbling through the keys tonight. Okay, 13.5 is our final answer. And 3 sig figs, we have 1, 2, 3, 1, 2, 3, 1, 2, 3, so the answer will be in 3 sig figs, 13.5 meters per second. That is the final answer to part A. That is how fast it will be moving after 5 seconds. If we look back at part B, it says, how far does it travel in this time? Alright, so look back at these equations, and you can see that was the one we just used, and we're looking for how far does it travel in this time now. So we're looking for a distance. Well, you have either this one or this one to use, because we're solving for distance. And let's look at our sheet. You've actually solved. It gave you three variables to start with: velocity initial, acceleration, time, and you solved for final velocity. So you now have 4 of the 5 variables that are in the kinematic equations. So you can use either one of these. Get back over here. Either one of these will be fine. You could use this one or this one, and you will come up with the exact same answer. In this one, you'll just be substituting your time in for t. In this one, there's no time mentioned. You'll be substituting a in for acceleration. So it's up to you whichever one you want to use. I'll go with the second one, and we'll go back to the sheet and I'll have it set up for you. Okay, and now I have it set up for you. In this equation, we're using distance equals our final distance equals the initial distance plus our initial velocity times time plus 1/2 our acceleration times time squared. So remember, you have these variables up here already. So let's just plug in what we know. For distance, we don't know our final distance yet. That's what we're trying to solve for. How far will you travel during this time, the 5 seconds? So our initial distance is 0. We hadn't gone anywhere prior to that 5 seconds beginning, so our initial distance is 0, plus our velocity initial was 1.50 meters per second, times time. Time is 5 seconds. Then plus 1/2 at squared, plus 1/2 our acceleration is 2.40 meters per second squared, times our time squared, which is 5 seconds squared. And that's supposed to be an S. My S's sometimes look like 5s. Anyway, this is our equation set up now. Let's give us a little more room to work with. Okay. Now we'll just do our math and solve. X equals 0 is gone. We need to find out 1.50 times 5. So let's take this step at a time. 1.5 times 5. And that will be 7.5. And our seconds will cancel out because these seconds are on top, these seconds are on the bottom of the fraction, so our seconds cancel out. So this is 7.5 meters plus 1/2 times 2.40 times 5 squared. So 1/2 times 2.40 times 5 squared. And that equals 30. 30 what? Our seconds squared will be on top, seconds squared on the bottom of the fraction, so both seconds squared cancel out, and we're just left with meters again, which is great because that's the only way you can add units together is if they're the same. So 30 meters plus 7.5 meters, our distance in that 5 seconds is 37.5 meters. And I know it's easy. When you look at this, it's all long and drawn out. I wrote my units, wrote my units, wrote my units, wrote my units. It's long and drawn out to do that, but at the end of the problem, it is a nice sanity check to be able to check your units and make sure that you're on the right path. Because if I would have come up with meters per second for these units and meters for this one, I would know I cannot add those together. You can only add together like units, right? So coming up with meters and meters, watching them cancel out up here, 37.5 meters, my final answer. That makes sense. So that is the answer to this problem. Let's see. Oops. How far does it travel in this time? It travels 37.5 meters.